Okay, let's start.
Good morning, everyone. So I'll be summarizing the lectures 146 to 148 today. So, previous to 146, lecture 146, we were discussing ways to map compute from uh, two different processors and we put up constraint equations and we were trying to uh, come up with some examples and see like how it is working. So this week we will go through a generalized algorithm for doing the same. So the algorithm for finding the highest ranked find partition, which is synchronization free, right? So we want the highest ranked one because we don't want to partition the whatever compute we have onto a relatively conservative small set of processors, and we want to do a better job and maybe use as much as processors we can. So that's why the high rank comes in. So basically the input to our algorithm would be a program with a fine array accesses, and we intend to output an partition. So now to allocate two sets of uh, two dynamic instances of an iteration, to be able to put them on the same on different processors, there needs to be no data dependency between them. If there is a data dependency between two statements, then we need to put them either on the same processor, or we need to have some sort of communication channel going between them. So how do we know, we are trying to put up a model, and how do we know whether there is a data dependency or not? So we have this tuple f1, say for statement s1 we have a tuple capital F1, small f1, capital B1 and small b1, which encodes the access, and if two accesses satisfy this condition that we have in this if f1 I1 and plus the small f1, and then f2 I2 plus small f2, it means that there is a data dependency between them. And if there is if there is a dependency, then we need to ensure then this constraint needs to be satisfied, which is like C1 I1 plus C1 is equals to C2 I2 plus C2. So now our job is to be able to come up with a method to solve these constraints, given this f this the previous equation on an axis is true. So we try to set up the equations so that we can solve them. So we change the notation of the axis representation, and we can write it as in this form. It is a more succinct way to write it. And if we bring everything of this equation on the LHS, then we can see that we'll have something of this sort of representation. So now we can use once we have that, we can use Gaussian elimination to eliminate as much as many variables as possible, and we are only the ones that are absolutely needed. Those ones would be left. So so. We argue that we can represent the same information using a lower dimension index variables, which is like t. So we argue that we can have a matrix U and then T, which can represent the same information, and T can be at a lower dimension. So having a lower dimension representation will help us to solve the constraints in a more like controlled manner and easier manner. So we substitute the previous slides equation and with U and T here, and we get this, and we argue that this equation should hold for all t's. So therefore, this part of the expression, right, the one with involving the constraints and the U matrix should be equal to 0. So once we have this, then we can solve this in classical like LP way by expressing it as AX equals to 0, and then we can solve for the unknown coefficients that we need for our partition. So let's go to like see like what a sample like U and T look like. So a sample U and T uh, basically will look like something like this. So suppose here we have so F1 is basically something which is which is encoded as like I plus is I plus 0 j, and I it is I and I plus 2j basically, and F2 is something which is like which represents like I plus j, and we brought it from RHS to LHS. That's why this negative sign is there. And the difference between the two additive constant evaluates to this vector 0 and 1. So so if we we had, say, suppose we have four unknowns, right, and our task is, we were arguing that we can represent it in a maybe in a two-dimension representation. So we are trying to just achieve that. So we have like four unknowns, and then uh, and two are only linearly independent. So therefore the degree of freedom is 2. So hence we can represent it in lower number of variables. Uh, so So this is the example. So if we do the math of multiplying, and then we can see that this I prime and j prime are basically functions of I and j, and we can represent the same. We can represent each of them using some common variables t1 and t2, and thus we reduce the number of variables. We don't need to have so many variables, and this will help us solve the space partitioning constraint problem. So I have one question. Um, sir, is this just like going to help us with the complexity of solving the solution, or like is there anything more to it, like reducing the number of variables?
Oh, reducing the number of variables is going to give you a higher rank solution eventually, right? I mean,
Yeah.
if you don't reduce the number of variables, you're basically not using the if clause at all. So, I mean, the space partitioning constraint was saying if this is true, then if X is true, then Y must be true.
Mm-hmm.
If you don't reduce so you're reducing the numbers, the number of variables using X.
Mm-hmm.
And then you are basically saying, okay, what's the maximum rank solution for Y,
Mm-hmm.
right?
Okay.
And
Mm.
after the
Okay.
reduction. So the whole, I mean, basically what we have done is we have summarized X by kind of reducing variables. If we don't reduce the variables, then we would be remaining with the original set of variables. And that would basically say that, that would basically transform the space partitioning constraint to saying, oh, Y should be always true, irrespective of whether X is true or not.
Okay.
And that is, and the maximum rank solution for that would be smaller rank, maybe even 0. Right? Than the maximum rank solution if you incorporate X. So X is basically helping you reduce the rank, reduce the rank of the space that you are interested in. And that's very important, right? Otherwise, the solution you get is not the maximum rank solution at all.
Correct. So moving on. So we go through one example of like how we proceed from by like solving this constraints equation that we had seen previously in the generalized algorithm, and so we put the example U matrix that we were seeing in the previous slide, and we multiply it with the constraint the variables, and we see that we can get to this set of values, and eventually we are able to we are able to find specific values for the different constraint variables. And like if we recall, like previous to this lecture, we had seen some examples where we were just assuming some of the we were saying that okay, this would be the values and we'll come to it later. So this is how this algorithm works and computes this set of values. So sir, I have one doubt here. So I was going through this. So this basis vector thing is also like if you could just speak like a little bit about it. So
yeah, I think this is okay. So basically, so first of all, we are interested in finding a maximum rank solution where the rank is on the C's now. For this equation that we have shown, Ax equals 0, are also shown in green for the example on the right. So this is the equation that we get, and we want to find the maximum rank solution. Now, when I say it's a maximum rank solution, what is the rank on? We want the maximum rank for the coefficient matrix, capital C. That's what we care about. We don't really care about the small c, right? I mean, it doesn't. I mean, it doesn't make sense to say that, oh, I want the maximum rank solution for small c. I mean, that doesn't make sense. It's only the capital C that you want the maximum rank for. Okay. So first of all, you have these. You have this set of equations, and you want to find the maximum rank solution for this. Now, the first observation here is because you don't care about the rank of the small c's, you can just set the small c's to 0.
So
it's like saying, okay, it's like saying this, right? I mean, so I'll give you an example. So let's say I have x minus y plus z equals 0. Let's say that's what the constraint evaluates to, right? And I'm interested in finding the maximum rank solution for x minus y plus z equals 0. Okay. So I can do that. What will I do? I'll say, okay, there are 3 variables. There's one constraint. So most probably, I mean, so basically the rank of the solution is going to be 2. Right? I mean, basically it will be 2-dimensional space. I mean, it's a plane, right? X minus y plus z equals 0 represents a plane in 3-dimensional space, x, y, z. And so that's the rank of the solution. And then what are the basis vectors? Well, you can basically choose any 2 basis vectors that whose linear combination represents that plane. Right? That's what basis vectors mean.
Okay.
But now I change the problem a little bit, okay? And I say, okay, I want the maximum rank solution in x and y, and I really don't care about z.
Okay.
That's what this problem is, really. I mean, because I really don't care about the small c's. I want the maximum rank solution for the capital C's. Okay. So this is the problem. So what do? I just set z to 0.
Okay.
And now I find the maximum rank solution for the remaining equation, which is x minus y equals 0. Now this is an equation in two variables and one constraint. So what is the maximum rank solution I'm going to get? A one-dimensional space, which is a line, right? Something like x equals y.
Okay.
Okay. And now, so the basis vector for this line would be, let's say 1, 1 or something like that, right? I mean, basically it's a single basis vector that basically represents the entire line.
Okay.
So now I'm going to, choose some basis vector. So let's say I chose 1, 1. By the way, I could have also chosen 3, 3 or 2, 2 or 7, 7, whatever, right? So I choose some basis vectors based on this constraint that x minus y equals 0. Let's say I chose 7, 7. Then I go back in the original solution to find the value of z for this solution that I chose. Right? So this is what this is basically saying, that you have this constraint which is capital AX equals 0. You first remove all the small c's because those are just additive constant. You don't care about their rank. And you get a new set of equations called a prime x prime equals 0. You find the basis vectors of a prime x prime equals 0. And then once you find that solution, then you go back and kind of say, okay, now I can just replace. I mean, I can just find what should be the small c's values in the original equation, because the new equation doesn't have small c's, but the original equation had small c's. So basically, go back and find that.
Okay. Thank you.
Yeah, this is a subtle point, and I think I didn't really go into detail. I mean, in my lecture modules, I realized this yesterday as well. So I hope this explanation makes more sense. And I'm happy to take questions on this part of the thing. I should point out that these are just mechanics of how to solve this. I mean, basically the problem that we have now is I need to solve for this equation AX equals 0 such that I get the maximum rank on some subset of the variables of X. So those subset of the variables of X are basically the capital C's. I really don't care about the small c's.
Okay.
If I wanted the maximum rank solution on all the variables, then we know it's a null space, right? I just find the basis vectors of the null space of the whole thing. But now the problem is slightly kind of modified, which is that, okay, I want the maximum rank solution only on these variables of this subset of variables in X, and the rest I don't care about. So what I do is I set the rest of them to 0, and then find the basis vectors of the modified equation a prime x prime equals 0.
Sir, one more question. So, why do we think that the small c's are not going to matter that much?
So, I mean, see, what are we interested? So, what is the processor space? Capital C into small x plus small c. I mean, right from the beginning, we have been saying that we want to maximize the number of processors in the processor space. So, how do we maximize the number of processors? Is small c going to matter in kind of determining the size of the range of this function? No.
Okay.
Is capital C going to matter? Yes.
Yes. Okay. Thank you. Sure. So moving on. So once we are able to find these constraints and what we want to do, once we have the affine mapping from the iteration space to the processor space, the next thing that we want to do is come up with a code generation scheme which will help us to actually execute whatever scheme we have, the partitioning scheme we have realized. So we'll go through that in this lecture. So so here for an example, we have two iteration sets, and S1 and S2, and then we have affine functions expressed via this C's, and then we have the processor space. So it is a function, and this C is mapping from iteration space to the processor space. And now we want to make sure that the code we are able to put the code together so that it makes sense to make it amenable for parallel processing. And what we do is, suppose this was our original program, uh, uh, two level of nestings, and we want to make sure that this gets placed on a set of processors. So we have to generate a loop. We need to have a loop which basically is kind of scheduling this code across processors, and the loop going over the processor would be like kind of data parallel. So there is no dependency across the iterations of the processor loop, and we can just blindly place it once we have this processor iteration loop, we can blindly place the body according to whatever processor ID we think it can go to. So how do we do this code generation is what we are going to discuss. So one thing in our scheme is that at the top level, at the processor ID iteration level, there is not going to be any data dependency. All the data dependency is going to be in the inner loops, and this will help us from locality perspective also, and the generated code will be easily amenable for parallelization across different processors. So we'll take this classical example that we were using all through, where we have two statements and we have like two level of nesting, and so basically the I comma jth iteration of statement S1 is going to run on processor ID determined by this expression I minus j minus 1, and similarly the the I comma jth iteration of statement 2 is going to run on processor ID which is evaluated by this expression, and we got this from our constraint solving algorithm. And we now, after solving those whatever constraints we had, we come to this conclusion, and now we know that okay, which iterations can be executed on which processors. So now what we want to do next is, like, we know which iteration which statement is going to execute on which processor, and if we see this was the original code, and this is the generated code that we are trying to come up with. So one thing we definitely need to do is, like, not all statements are pass the criteria of execution on every other processor. So only certain processors are going to be valid, only certain iterations are going to be valid for certain processors. And how can we achieve that? So one scheme is to just allow everything to run, but predicate with some conditions this statement. So if we know the processor ID, we can predicate it with the criteria. So which is like p equals I minus j minus 1 for statement 1, and for statement S2 we similarly do p, we check for p if p processor ID is equals to I minus j. Now the thing is, now what we need to come up with is, like, how is this p going to get determined? And for that, the we need to know the bounds of the processor loop and the processor ID loop. So how are we going to determine the upper bound and lower bound of this processor iteration variable p? So we'll use the Fourier Morskin method for that. So how do we come up with this the bounds of the processor in iteration variable p? So there is an algorithm for that, and what we do is, we generate the outer loops for processor ID with depth equal to the max rank of coefficient matrix across all statements. and we identify the lower and upper bound for each dimension of the processor ID, and we do this for each statement separately, and then we merge the solution for all the the statements that we get, and we put them together. So, and then finally we update the so whatever was the original program, we just embed it inside the processor loop that we generate, which is basically like having the correct upper and lower bound, and we also make sure that we predicate the statement so that they don't execute on the wrong processor. So so let's take an example. So yeah, so first what we do is like we use the Fourier Morskin method on S1 like to project the range of J on this inequality P plus J plus 1. So basically this was basically I is this was I is greater than 0 and less than 100, and then we just do the like substitution here using this equation, and we get P plus J plus 1. So we substitute it here, and then we do the Fourier Morskin Fourier Morskin method on these two inequalities, and we can eliminate J also. So if we like do the math, then we'll get two inequalities. P is less than equal to 99, and P is greater than equal to minus 101. So that is how we derive the range of the processor iteration variable. And so we also do the same for S2, and then we take the union of these two inequalities, and we get to the final bounds. So basically now what we have is like we have done so first we came up with the partition constraints set of constraints, and we knew that okay what would be the processor mapping functions, and using that we know that okay certain statements need to execute on certain processors, and we predicated them. And then we also derived till now and we have also derived the processor range loop bounds. So we have done up to now we have done this. Now we so what now we have certain quality of code that is correct, which is that got generated, it is correct, but certainly we can optimize further. So we are going to look how we can optimize further. What could be the suboptimalities and how we can optimize further on this generated code. So one thing is like the code that we generated is like pretty relaxed here. So it is correct, but it may not be very optimal because we are like going through lot of still we are going through lot of iterations, and lot of them are like kind of redundant because only certain iterations are going to be actually be effective. So we are trying to optimize that. So yeah, so we had identified the space partitioning constraint. We have solved the space partitioning constraint to obtain max rank function from iteration space to processor space, and then we did the code gen that makes the outer processor loops parallel and inner loop sequential and predicates the iteration processor validity criteria. So we have something which is correct till now. Now we want to optimize it further. So if we closely look at this program that we were studying, so what we see is like the innermost loops, right? Lot of them will be empty iterations because only few of them are going to pass the criteria of execution on a particular processor. So how we can optimize them. So we call this as tightening of loops, and we want to reduce the amount of work without changing the meaning of the program. That is basically optimize the program. And how do we do that? One more simple example that we take is like this looks like a very embarrassingly parallel program, and we can just blindly schedule it on a set of processors. And so if we just look at this, and if we look at the transformed code, right, according to whatever algorithm we came up with in the previous slides, right, so we'll get something like this. But here, like most of the iterations are going to be empty. So I think only two iteration will have some effect, and most of them are going to be empty. So we can try to tighten the bounds of this inner loop, so that we have like much lesser number of empty iterations. And how can we do that? So we'll try to use Fourier Motzkin method to find the upper and lower bound, and we'll do the appropriate projection for each statement. So suppose we start. Let's take an example, and we'll try to see how we can do it for statement S1, and then how we can extend it for like in general. So for S1, if we notice that, then we have a set of constraints uh, uh, that need to be true, right, for it to execute. So one constraint would be this which is coming from the processor loop. Other constraints are coming from the other two loops of I and J, and then we have the criteria. I think I missed this criteria has been splitted into two inequalities. So I think I missed the other part. So we have this set of constraints, and then what we try to do is like we want to use a Fourier Motzkin method to project on other dimensions. So after say how we do this, what we try to do is like we fix P, and we try to project remaining dimensions uh, on I, and from there we get the upper and lower bound of I in terms of P. So that is how we get these two inequalities, which is I is greater than max of either 0 and P plus 1, and I is less than min of 100, 100, 1 plus P. So this is how we get the criteria for statement S1. Similarly, we can compute the same thing for S2, and then so similarly we can compute the same for S2, and then what we want to do is like we want to take we want to somehow merge these two results, so that it is applicable for both S1 and S2. And how we do that? We want to take the more liberal choice on each dimension. Whatever we derived, we want to do that. So for an example, so S1 we had seen in the previous slide, we got this, and for S2 similarly, if we do the mechanics, then we'll get this. And then for each dimension we want to just have a more relaxed bounds. So for the first dimension on P, it is same. So the result is also like same. And on the I dimension, we see that max of 0 and P we have. For S2 we have max, we have to I should be greater than max of 0 and P, and for S1 max should be 0, I should be greater than max of 0 and P plus 1. So basically, which is more relaxed? I think it will be max of 0 and P. is more relaxed. And similarly, we try to find what is more relaxed between these two conditions, and we see that like whatever like allows more values, we choose that one, and hence we in this way we are able to generate the same for like the overall thing for both including S1 and S2. And then we go and update the bounds. So whatever we have computed from here, we go and update it. As we can see, we cross out the original bounds, and we have more tighter bounds now, and which will potentially give us much more optimal execution. So think I think I had this, and then beyond this we can optimize the tests which I have not been able to cover. So maybe I will take Sir's help to walk us through.
Okay, thanks, Saurabh. So yeah, I mean, basically, are there any questions so far? Basically, we talked about how to solve the space partitioning constraints in general. Then we talked about how we could, once we have the solution to the space partitioning constraints, how do we generate our first version of the code, which is a naive code generation strategy, where we just kind of put outer loops to be the processors and just stick the whole program in as it is, except that we predicate each statement so that it executes only on the right processor ID, and or on the corresponding processor ID, I should say. And then finally we now, but this doesn't look like a very good solution because we've just added more loop iterations and made the program even slower on a single processor. And even on a multiprocessor, we haven't really made anything faster now because we're just going to execute so many iterations. The good thing is many of those iterations are going to be empty iterations because of the predicates that we have put. Some of those many of those iterations are just going to be no ops pretty much. And so the question is, how do I tighten the iteration space? And the answer is really just our Fourier-Motzkin method, right? So basically we put our constraints, whatever are the loop bound constraints, and then in addition we put the predicate in. And so we have this bunch of constraints, and then we project these constraints on the dimension we are interested in. And then we keep doing this, from the outermost to the inner one to the more inner one, and so on. And so we get tighter loop bounds because of that. So that's just elimination of empty iterations using the Fourier-Motzkin method. But because the predicate could have been different for each statement, we have to do this for every statement separately, right? And so for every statement, we will get a polyhedral space as the tighter space, right, which has all the empty iterations eliminated. But now, because if these statements are going to share the same loop, then we need to take a union of these two polyhedral spaces. And in general, like union of two polyhedral spaces may not be polyhedral, right? For example, in a single dimension, an interval is a polyhedral space, and I take a strict union of two intervals, then I don't really necessarily get a single interval. So, to solve that problem, what we do is we just kind of find the tightest polyhedral or tightest interval that contains both these intervals. So in other words, take the minimum of the first interval and the maximum of the second interval, and kind of that's the more relaxed union, and that's what Saurabh was talking about. So that's so good, so far so good. But even still, I mean, so I mean, now we have made some progress in the sense that we have made the program almost equal in its number of iterations compared to what it was originally. Yet we have moved all the data independent iterations in the outer loop and all the data dependent iterations in the inner loop, which means we can both do parallelization and locality. And the total amount of work that we do in terms of the number of iterations we execute is almost same, right? But I say almost because we still have this interval issue and all that kind of thing, right? But now there's still room for improvement because we are doing lots of kind of if then else kind of checks, right? We have this predicate which looks ugly when you read the code. That's number one. But it also kind of adds a little bit to the overhead of the execution. And that overhead is not kind of measurable in order n or something like that. It's more like it's more like the constant part, because it's not like we are doing any kind of asymptotically worse than the original program now. But there is these small kind of constants that also matter, because from a compiler's perspective, you want to optimize even these small constants, certainly. And so the idea here is that, okay, now we have this code which is kind of general. Can we kind of, special, can we kind of, let's assume that code size is not an issue. So we kind of make multiple copies of this code and kind of split my iteration space into multiple smaller sub iteration spaces or smaller intervals, such that for each interval I have fewer number of checks that I need to do. Okay, so that's basically the idea. And there again, basically, let's say there were multiple statements. So most of the issues are coming because of multiple statements. If there were no multiple statements, if there was only one statement, then everything was anyway polyhedral, and we were actually okay, completely okay, because what we would have got was that the outer, we would have got a 2-depth loop nest. The innermost loop would have been a single iteration, and that just doesn't count. I can always replace the single iteration with a simple statement, right? I mean, completely get rid of the for loop at all. So if it was only a single statement, everything was anyway we are already almost done. Okay, but it's all only because of multiple statements that all these kind of complications are occurring. In the example that we showed, there were 2 statements, and because of that, the inner loop would have up to 2 iterations. Sometimes it will have only 1 iteration. Sometimes it will have both iterations. Sometimes the inner, sometimes it will have both iterations. And in some of those iterations, both statements will execute. In some of those iterations, only one will execute, and so on. Okay. So so basically the idea is, let's specialize, right? And the idea is, okay, let's try to make intervals at each dimension. So let's say I take the outermost dimension. So it's from, let's say, -101 to +100. So I say, okay, is it true that both S1 and S2 execute in all those iterations? What do I mean? I mean, is it true? Because after all, it's not just the outermost, but they are also innermost. So for any value, let's say I take any value between -101 to 100 +100. Let's say I take the value +5. Right? So I take the value 5. Is it, for the value 5, do there exist values of I and j for which both S1 and S2 execute? Okay. Now, similarly, I ask the question for, let's say, -101. For -101, do there exist values of I and j such that both S1 and S2 execute? Okay. And so the answer we'll get is that, oh, for for the leftmost part, actually in this case, just the singleton interval, which is -101 singleton point for P, only one of the statements executes. Let's say it's S1. Then from -100 to 99, there exist values of I and j for which both S1 and S2 execute. And then for the last point, which is +100, only S2 executes. That's the idea. So basically, what do? I split the outer loop into 3 parts. First, where P is equal to -101. Second, where it's between -100 and 99. And third, where it is equal to +100. So for the -101, I can specialize the code because I'm sure that there exists no value for S1 and S2. There exists no value for I and j such that S2 executes. So I can just kind of actually get rid of the S2 completely. Also, I can tighten the loop bounds now with the knowledge that P equals -101. And when I tighten the loop bounds, you're going to actually find in this example that I and j also become singleton sets. Okay. And so that just becomes a single kind of block of statements without any loops. So that interval becomes a block of statements. Similarly, the last one becomes a block of statements without any loops. And it's only the middle one that remains. And the middle one is homogeneous from P's perspective because there is, in this entire range, there exist values of I and j for which both S1 and S2 execute. So now let's do the same thing. So the 2 corners have been settled. Now it's only the middle one that's a problem. We have homogenized for P. Let's do the same thing for the next dimension, which is I. And we're going to find something similar that I also we can kind of divide into 3 partitions or something like that. And the kind of the 2 corner partitions are just going to be very easy. And it's just the middle partition that matters. And for the middle partition, we can be sure that both S1 and S2 execute. And because both S1 and S2 execute for the middle partition, we can actually get rid of many tests. For example, we can even get rid of the inner loop and just kind of paste S1 and S2. And we can get rid of the inner loop and the innermost loop on J, and we can get rid of the predicates because we are sure that S1 and S2 will execute from here on. Right? Something like that. I mean, I've skipped a couple of steps. For example, I actually, strictly speaking, I should do the same thing on J as well after that. Okay, but I mean, I'm hoping that, okay, for J, there will be no partitions whatsoever, and the entire J space is going to say that S1 and S2 both execute all the time. Okay, in case there were partitions in J as well, we were going to do the same thing. So at the end of the day, we're going to find these kind of corner elements for P, I, and J, and then this inner loop, which basically we have avoided the tests. And so we have increased the code size, but the inner loop now has fewer tests, much fewer tests. And so, and that's what matters, right? From a performance point of view, we want to optimize the innermost loop. We have increased it at the cost of code size. So that's basically the idea.
Thank you, sir.
Thanks, Saurabh. Yes. Yeah. So thoughts, questions, discussion. Yes, Jay.
So, sir, I wanted to ask that. We discussed in the first module that so we reduced the equation to a matrix which had all the unknown coefficients into a matrix U equal to 0, and we wanted to find a solution for that. So we got that equation for one pair of axes which were data dependent, and we may have more than, I mean, we have more pairs of data dependent axes, so we'll have more equations just like that. I mean, and for those equations, the U matrix may be different and this coefficient matrix may have different dimensions. So what was not clear to me that how would we handle multiple constraints and find a solution that satisfies both of the constraints?
Okay. Thanks for that question. So firstly, like the capital C's and small c's are different for each statement anyway. So we find different C's and capital C and small c for each statement, right? And we don't need to combine anything. I mean, so we don't need to combine anything here. So for S1, we find capital C1 and small c1, and that's it. And we are done. Now for S2, we find another capital C2 and small c2, and we are done. And for each of them, we have to solve this, for this kind of, in this way of using the Gaussian elimination and all that kind of stuff, right? So does that, I mean, I don't know if I understood the question correctly.
Yeah, I guess so. When we solve one of the equations and then express it and put it in the other equation, so I guess that will solve the.
But aren't we solving for both C1 and C2? Like when we take the C1I1 plus C1.
The C1 and okay, I see. We're saying we're looking at one pair of axes. I see. Okay.
I mean, like in the example that we saw before. So
I'm sorry. I got this wrong. Okay, cool. So you're looking at one pair of axes, and then we solve for that, and then we have to look at another pair of axes, and we can get. Okay. Yeah, right. I mean, so we need to combine. So I guess in the example that we used, there was only one pair of axes that we worried about. And so it was all okay. And we kind of just, went ahead with that. But let's say there were more pairs of axes that were kind of consequential. Then what we'll have to do is we'll have to constrain. So we basically got this AX equals 0 constraint for one, that is one constraint. Then we take another pair of axes, we get another constraint, which is A prime, let's say A2 X2 equals 0. Right? Get another constraint A3 X3 equals 0 and so on, and then we can just kind of merge them into a single one, which is AX equals 0, because all the rows of A can be kind of combined into a single matrix A, And X is going to be the common thing here, which is just the unknowns, capital C1s and small c1s, and capital C2s and small c2s. Yeah, that's a great question. Thanks for that question. So if there were multiple pairs of accesses for which we have to solve the space partitioning constraints, then for each pair of accesses, we get a separate set of equations. And at the end of the day, we want a solution which satisfies all these equations. So it's an intersection. And so the way to represent it is, for one pair of accesses, you got AX equals 0. Let's say, let me say you got A1 x1 equals 0. For another pair of accesses, you got A2 x2 equals 0. So what you really want is that you just kind of, actually you got A1 x equals 0 and A2 x equals 0. X is common in both of them. And so you just kind of combine them and say A1, A2 of x equals 0. So you just combine A1 and A2 into a single matrix. That's what it is, right? Yeah. I hope that answers your question, Jay. Or
Is the X common to both of them?
Well, I mean, yeah. For example, if we are talking about the same, okay. So yeah, let's assume that X is kind of, sure, X is basically all the C's, right? So let's say there were three axes, C1, there were three axes. So there will be X1, X2, X3. So one pair of constraints may give you a constraint between X1 and X2. And so all the coefficients of X3 in those rows will be 0.
Okay.
Right? And then another pair of accesses will give you constraints between X2 and X3, in which case all the coefficients of X1 will be 0. And so you can put them into a single matrix, right? Yeah.
And I had another question. So, we kind of assumed in the analysis up till now that the loop iteration variables are local. So what would the compiler have to do separately if the loop iteration variables were not local? I mean, if let's say these iteration variables were live after the.
Oh, if the loop iteration variables were live, then that's an easy problem here, right? Because I can just basically, because it's a polyhedral space, so I just know what's the last point of this polyhedral. I know the ascending lexicographic order, and so I already know what the last point is, and I just kind of at the very end just set those loop iteration variables to that last point values, and we are done. Right? Is that?
Yeah. So I was just wondering. So that's the only thing that we would have to do, right? I guess. Okay.
Yeah, I mean, it's all about just kind of preserving the values of the loop iteration variables here, right? And so what will be the, at the very end, what will be the values of the loop iteration variables is pretty much the last point that gets executed in the iteration space. So internally, I can modify whatever I like, but at the end, if I just set those loop iteration variables to that value, even though that particular point may have executed somewhere else, maybe in the beginning or in the middle or something like that, at the very end, I just set it to that value and we're done.
Okay, thank you.
Sure. Yeah, Setu.
Yeah, hi. So when we were computing the loop bound, so we had this coefficient matrix times some u is equal to 0. And then we start from that and we simplify that to a matrix of the form Ax is equal to 0, right? Where x is the vector of all the unknowns. Now, in the example which we took, this capital C and capital C2 were actually just a single row vectors. But in general, they could actually be matrices, right? So what we are trying to find is this coefficient matrix will not be it would not be a single row vector. It could very well be a matrix times some other matrix u is equal to 0, right? So the way I see it is that we just matrix multiply both of them, collect all the coefficients of the unknowns, and then using that create a new matrix A, and then x would then become C111. So like capital C1 and then the first element 11 of it, and so on and so forth, right? Just to be clear, is that what we are trying to do?
Yes, and even in the lectures, I mean, I never said that capital C1 is a single row. In fact, even in our example, capital C was 2 rows, if I recall correctly, right? So yes, I mean, but right? I mean, did I get? Was
So
it 2 rows?
I think in the lectures, you never explicitly said that it would be a single row vector, but I think the example which you took only had a single row vector.
I see, because we basically assumed that one row is going to be like a one-dimensional processor space. Okay, got it.
Yes.
Yeah, true. Yes, but yeah, in general, yeah, of course, I mean, it can be a multi-dimensional, and in fact, even for this example, the computer algorithm will assume that it's a two-dimensional processor space. only the later solution is going to find that the maximum rank solution can only be one rank 1 and not 2. So I mean, it's actually going to be, I mean, we just simplified it in our discussion just to make presentation easier, that we just said, okay, we already know it's a one-dimensional, so just use one dimension. But in reality, it's going to be two-dimensional, and indeed, it's a matrix multiplication between that capital C1, minus capital C2, and so on, with the U is a matrix multiplication. Absolutely.
So a follow-up question on that. So we claim that if we can find the max rank solution of Ax is equal to 0, then that would also be the max rank solution for this coefficient matrix times U is equal to 0. Now, the way I see it is that...
No, hold on. Basically, we are interested in, so Ax equals 0. Basically, here x's are basically containing both capital C's and small c's.
Right.
Right.
So just a moment. So
Sure.
x is a vector, right?
X is a vector.
So when you say it contains capital C, it just means that it contains the elements of capital C, right?
It contains the elements of capital C.
Right. Go ahead.
It contains the elements of capital C in some arbitrary order. We don't even care about the order. Okay. It contains the elements of capital C and small c in that vector X. Now we are interested in finding the max rank solution for X.
Right.
Actually, for a subset of X, we want the max rank for capital C's only. We don't really care about the small c's. So we want to find the max rank solution for a subset of X, such that this equation will be true. In other words, we want to find the null space of A.
Right.
Right. We want to find the null space of A, and we want to maximize the rank of the capital C's in that null space.
I see. Got it. Thank you.
Thanks for the question. Okay. So, all right. So, yeah, let's see what else can we discuss here. So I mean, basically, we have learned about a method to transform a loop nest, which first kind of bring it into a polyhedral form, and then analyze its access pattern, and then basically understand its dependencies, and then based on the understanding of dependencies, reschedule the iterations such that the dependencies have smaller reuse distance. They come into the inner loops. So that's that's what these space partitioning constraints encode. And then we solve these space partitioning constraints. The other thing we learned is how to do code generation, which is actually a very mechanical, but mechanical method, in the sense that you just have to kind of do one thing after another. I mean, we learned the algorithm at least to how to do this. I mean, it's of course very tedious to do this manually. And yes, I mean, it seems like a very powerful method, in the sense that it actually, firstly, before you understand this stuff, you feel like this is almost magic, as basically, because it looks like it's it's such a complex amount of reasoning that somebody might have used. But at least now, I mean, now we have been able to reduce it to some kind of mathematical constraint solving problem, which can be solved in this way. Yeah, let's see. I mean, what is the complexity of this constraint solving procedure? It's not that bad. I mean, just using Gaussian elimination, and then we are identifying the null space and things like that. So most of the things are basically linear algebra like, basically. And but of course we are also under the constraints that these are integers, so it becomes integer linear programming kind of settings. All right, and I guess we have kind of learned the basic kind of tools to basically do these kind of reasonings. Our next set of modules are going to be, I would say, lighter, in the sense that we're going to look at examples of transformations that for small loops and small kind of things which we call primitive affine transforms. I'm going to see how these primitive affine transforms are automatically derivable from these space partitioning constraints that we have learned. Of course, space partitioning constraints can do much more than the primitive affine transforms, because it's a general method for any kind of loop nest. But when we kind of look at some particular loop nest, then this is what happens, and so this is the transform that happens. And we looked at things like, loop reversal, loop skewing, or fusion, fission. It turns out that all these transformations can be expressed as synchronization-free parallelism problems. And because they can be expressed as synchronization-free parallelism problems, the space partitioning constraint-based solution can be applied to them, and what you get as a result is exactly the transformation that you otherwise reason about, right? So with the exception, so I mean, there are many transformations that we have talked about in our previous modules, maybe in the much earlier in our course, things like fusion, fission, things like that. We've also talked about loop tiling. So loop tiling is one of those transformations that does not fit into the space partitioning constraints. Okay, and so that's something that we're going to touch upon later on, maybe in the week after, on how that can be done, and that's that fits in the topic of blocking. All right, and so blocking is not coming directly a transformation that kind of falls out from space partitioning constraints, but you would be, you would find it surprising and maybe interesting that many other transformations that we've learned for loops are kind of fitting into this loop partitioning, this space partitioning constraints example. I'll also say that there are two types of, I mean, there's another way to kind of categorize loop transformations. In one category of loop transformations, you don't change the order of iterations. If you look at loop unrolling, you have not really changed the order of iterations. You just kind of made the syntax different. You execute more iterations in a single loop. If you look at loop peeling, you just peel the first few iterations and execute it in the pre-header of the loop, and then basically even there you have not changed the order of iterations. If you look at loop splitting basically says if I have for I equals 0 to n, let's say some s1, you change it into for I equals 0 to n by 2, and then the second iterations, the second loop is basically for I equals n by 2 plus 1 to n. Right? So that's basically just splitting the iteration space into two parts and doing the first iteration here and the second iteration there. That's called loop splitting. Loop merging, just the opposite of loop splitting, where you kind of merge the two loops. So you have two loops, one is going from 1 to n by 2, the other is going from n by 2 plus 1 to n. You just merge them into a single loop and make that n. Loop unswitching, right? Loop, I don't know if you remember what's a loop unswitching. So you have a loop, and then inside it you have an if then else. And you figure out that the if condition is actually loop invariant. So you bring the if condition outside the loop, and you make two copies of the loop, one for the then body, one which is specialized for the then body of the if branch, and the other which is specialized for the else body of the if branch. Okay, so these are all transformations that do not change the order of iterations of the original loop. In other words, the iterations execute exactly in the same order as in the original loop. I mean, there's a rich set of transformations, rich set of very useful transformations, including vectorization and stuff like that, like unrolling and vectorization, peeling, and then peeling, unrolling, vectorization. In fact, I would say a large majority of transformations are transformations, and a large majority of transformations that actually get triggered for real world programs by typical compilers, typical modern compilers today, are transformations that don't change the iteration order of the loops. Okay, and these are actually easy, and so these transformations are easier to reason about also, because you don't need all this polyhedral framework and that kind of stuff. The transformations that we are learning about now through the polyhedral space are basically transformations that change the order of iterations, potentially completely change them, right? I mean, they can completely shuffle the iteration, completely reverse it, blah, blah, because we are actually now, basically saying, okay, just we can put in an arbitrary order of processors, arbitrary function from iteration space to processor space, and then we can iterate on the processors in any arbitrary order, and so on. And so that basically means that we're basically changing the order of iterations. And so those are if I look at that category of transformations, a large subset of those transformations are basically being captured by the space partitioning constraints alone. And so that's why space partitioning constraints is a very, I would say, very important and powerful technique, because I mean, large category, like for example, the affine primitive transforms that we're going to talk about in the next week, which include fusion, fission, reversal, skewing, and more, just kind of fall out from space partitioning constraint formulations, right? Yet there will be some such transformations which change the order of iterations, which do not get captured by space partitioning constraint formulations, such as tiling, also called blocking, right? And so
software pipelining, can it be done by?
Great example. So what do you think? Where does software pipelining fit in? Is it with? So I've created three categories.
Middle of like changing, like something like in the middle of changing the order, or like not changing, because like across iterations we are in the within the same iteration we are not changing the order, but across iterations, so the last statement of the previous iteration may get executed later with the first statement of the next iteration, something like that.
Okay, so software pipelining does not change the order of computation. It may kind of, change it doesn't change the order of computation. Yeah. So when I say order of iterations, I mean, I'm not really strictly saying that the iterations should remain preserved, right? More generally, I should be saying order of computation, right? So that's what I mean. So the first category is basically set of transformations that don't change the order of computation. So basically what in software pipelining, what happens is you kind of, let's say you have an iteration. So half of the iteration, you kind of move up and peel it out. So it's like half of the first iteration gets peeled out. And then the second half of the first iteration gets put together with the first half of the second iteration. I'll repeat this. Second half of the first iteration gets put together with the first half of the second iteration. I haven't changed the order of computation.
Correct.
So that software pipelining will come into the first category, which is, we didn't really change the order of computation.
Okay. What about unroll and jam? There also we are not changing the
unroll and jam. No, we are not changing the order of computation. Yeah.
So for loop switching, wouldn't we actually change the order of iterations? For example, so we have if some condition, else some condition. So if I peel the if out and then I do a loop and then I peel the else out and then I do a loop, aren't I doing like if1, if2, if3, blah, 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 and then else1, else2, else3? Whereas earlier I would...
If and else are mutually exclusive. When you do loop unswitching, then basically you have identified that the loop condition is loop invariant, which means for all the iterations, either only the then clause executes, or for all the iterations, only the else clause executes. It's not like, for some iterations then executes, and then in that case, you won't be able to do loop unswitching.
Okay, thank you.
Right? So even there, you're not changing the order of transformation, order of computation.
And sir, classical loop independent code motion, that also like that is also like kind of changing the
classical loop independent code motion. Yes, I mean you can argue that it changes the order of computation, but
it's only one type of thing.
It's only one thing. So that doesn't, I mean, in my model, that won't count as changing the order of computation, right? When I say changing the order of computation, it's like more macro level change of the computation order, right? Where basically, and here you're just basically saying, okay, it's like more like loop invariant code motion is more like caching, right? You just kind of cache some stuff up front, and so that's just like one thing you did up front, which is order one stuff that you moved up. So that's not going to count as changing the order of computation.
Okay.
Okay, great. Great. I think that's a great discussion, and let's stop here. I'll just stop recording first.